Hello guys, welcome to my YouTube channel. So today we are going to have our second lecture on Biopython. So in biology the basic tenets of central dogma it's are replication, transcription and translation. Now replication is very easy. You will have a one strand and you have to just copy the DNA. So that is very easy. So there is no point in just demonstrating it. But transcription and translation, both things are very important and they are worth mentioning. So suppose you have a DNA sequence. So today we will see using Python how can you transcribe that DNA sequence into an RNA, and also if you have an RNA sequence, how can you translate that RNA sequence into the corresponding protein sequence. So okay, so just as my previous lecture, if you have watched it, so you know that we have to install this Biopython first in Google Colab, or if you're doing on Jupyter or whatever, you have to install this, and then you can proceed with all the necessary functions. Okay, so we have installed Biopython here. Now we will perform the transcription. So for that, we have to import Biopython. So we'll write import bio, and then we have to import the sequence class from the biopython bio.asq module. Okay, so we will write from bio.asq import asq, because this sequence class is necessary because we will be dealing with the sequence. So we will create the DNA sequence now. So DNA is equal to, okay, asq will create one DNA sequence. Suppose A T G G 80 CC GC, okay, AG. So this is our DNA sequence. Now we will transcribe. So we will write RNA is equal to DNA dot transcribe. So this transcribe function will transcribe the DNA into the RNA and will print this RNA. Okay, and now we'll run this cell. So on the left hand side you can see it's running, and here is the result. So here is, you will see the sequence has been transcribed. Okay, and this was your DNA sequence and this is your output. So A, G and C remains the same, but in transcription what happens, in place of thymine you have uracil. So if you have a DNA sequence, so you can perform the transcription here and you can get the transcribed mRNA. Okay, so in the previous lecture I taught you how you can concatenate two sequences. Suppose you have DNA1 sequence and DNA2 sequence, you can concatenate them to create a third DNA sequence where it will have the sequence of both the DNAs. Okay, similarly you can concatenate a DNA and an RNA sequence also, but uh, like uh, that procedure is a little bit different. We'll see in our subsequent lectures. Now our uh, function is to translate this RNA into a protein. Okay, so suppose we are taking this RNA only, what we got in our result. Okay, so we are taking this RNA, and for translation we are writing protein is equal to RNA dot translate, and we are printing this protein. Okay, so let's see. So this MDIR, okay, so this is what you are getting. Do you know that this MDIR means this is the one letter amino acid code. Okay, M stands for one amino acid, D stands for one amino acid, likewise. Okay, so now this entire sequence has been divided into three codons, and it has been translated accordingly. So if you have a DNA sequence, from there you can perform transcription and then you can perform the translation also. So another thing that you can do here is, suppose you want to manually see the codon table. Okay, so how will you do that? For printing the standard table, standard codon table, we will use standard syntax in Biopython. So we will import the codon table class from bio.data module. Okay, so we will write it as codon table, and we will sorry, there shouldn't be any gap, and then we will write standard underscore table is equal to codon table dot unambiguous underscore DNA by underscore name within brackets standard uh, sorry, by ID. Okay, and within brackets I'll write it as 1. So there are two tables in NCBI which are stored there, and the table ID for standard one is 1. So we are recalling that table from the NCBI database which is stored in this Biopython module. So standard table is codon table dot unambiguous DNA underscore DNA by underscore ID 1, and then we'll print it. Okay, now let's run this cell. Let's see what happens. So yeah, this is the table 1 standard is GCO, which is stored in NCBI, and it is also stored in Biopython. Okay, so here, as you can see, this is what we mean by a codon table, and these are the triplet codons, and these are the single amino acids. So F means phenylalanine as far as I remember. So for phenylalanine, this is the like codon. Okay, similarly these are the codons for leucine. Okay, so these are actually the codons triplets, and these are the single letter amino acid codes. Okay, F, L, S, okay, H, and these are the stop codons as you can see here. Okay, so it has been printed with respect to the DNA. That's why you won't find any uracil here. So in general, the stop codon for uracil is UAA, but it has been printed with respect to DNA, so it has written TAA is stop codon. Okay, so anyways, so this is how you get a standard codon table. So suppose you forget what are the which codons code for a particular amino acid, then you can print it and directly you can see, and then you can write your code. So another thing is, you can, if you want to perform reverse complementation, okay, so that you can do it here. So suppose we will select this only, we'll select this DNA sequence. Okay, and then I will write it here again. So we have this DNA sequence. So before this we have to include one class also. So from bio dot sequence import reverse complement. Okay, and this is our DNA sequence. Then we'll write reverse complement DNA. So this will print the reverse complement of the DNA. So this is the reverse complement of the DNA. Okay, this is printed from the back side as reverse, and also the complementary strand. So reverse complement means the complementary strand of this DNA sequence should have T. Okay, but it is printed in reverse order, so T comes here. So likewise, the complementary strand of this should have A, but it is printed in reverse order, so it's A. Okay, so likewise. And the last thing, suppose we want to back transcribe. We have seen how we can perform transcription, but suppose we want to back transcribe it. So how will we do? Same again, we will see back transcription. So back transcription means you have the RNA sequence, you need to get the corresponding DNA sequence from which that RNA was transcribed. So we will use our result here only. Okay. So yeah, so this was our RNA sequence. Now we will see if we get the same DNA sequence or not. So let's go. So we will write from bio.sequence. So we need to import back transcribe class. Okay, and then this is our RNA sequence. Okay, and we'll write back underscore transcribe RNA. Now we'll run this cell. Okay, so this was the original DNA sequence that from which this RNA was transcribed. So see, you can compare this. I used it in the previous code also. So same sequence. So if you have an RNA, if you want to know the corresponding like template DNA from which it was transcribed, so you can get this through Python. Okay, we'll deal more of such lectures in our further videos. So stay tuned.